Hey folks, it's 9 o'clock on Sunday morning. I just woke up, I'm tired, and I'm going to make you a video. So I'm going to do my best, and I'm going to try not to make it super boring, but it's going to be kind of hard because I just woke up and I'm really tired. But anyways, we are going to be talking about rational functions, which are the ones that look like that. We are talking about fraction functions, so like 1 over x would be a basic example of one. So we are going to be dealing with rational functions. They have polynomials in the denominator and sometimes in the numerator as well. We're going to learn how they work. So the most basic rational function we could talk about would be y equals 1 over x. We all know that it looks like that, and it looks like that. Maybe you knew that there was a point right there at negative 1, and a point right there at positive 1, even though mine doesn't really look like it. It should go through that. Maybe you even knew that it had vertical and horizontal asymptotes at y and x equals 0, but maybe you didn't really know why. So now we're going to talk about why. So let's imagine that I zoom in on this purple part here. So I'm dealing with x values between negative 1 and positive 1. And let's see what happens to our graph. So let's pretend like we're at the point, say, x equals 1/2. Well, our function is y equals 1 over x. So when x is 1/2, y is 1 over 1/2, but dividing by a number is the same as multiplying by that number's reciprocal. So really I have 1 times the reciprocal of 1/2, which is 2 over 1. So really I just have 2. Well, let's move in even closer. Let's try, what do you say, an x value of 1/4. So then I'd have 1 divided by 1/4, which is the same as 1 times 4 over 1, which is 4. So when I move halfway closer, I'm already up here at y equals 4. So I'm growing pretty quickly right now. Well, let's try another one. How about 1/10? 1 divided by 1/10 is 1 times 10 over 1, which is 10. So as I'm getting closer, I'm getting absurdly larger y values very quickly. So I'm at y equals 10. So imagine going to y, or x equals, say, 1/1000th. Then when you're really close there, you're already up at 1,000. So I can't even show you that here. The point is, as I move closer and closer and closer to where the denominator of my function equals 0, in this case, x equals 0, as I move closer and closer to that vertical asymptote, my graph shoots off towards positive infinity on that side. And if you think it on the left side, my graph shoots down to negative infinity. That's what creates our vertical asymptotes. But that's not the only asymptote we have. We also have a horizontal asymptote. And to figure out where you would have horizontal asymptotes, you need to think about the value of your function. More specifically, the value of the fraction for given x values. So I just listened to what I had recorded so far, and I heard myself say fraction a moment ago. Man, my voice was not in peak form right there. Pretty high-pitched and cracky. Anyways, we were talking about the horizontal asymptote being created because we have 1 divided by a really, 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 really big number is essentially 0, but it's not quite. So we level out towards 0, but we never actually cross it. Because we have no x's in our numerator, our fraction can never be equal to 0. So now let's think about this function, which we know from last unit is going to look pretty much the same, but it is a horizontal translation to the right 3. So our graph is shifted to the right 3. And if you think about just the denominator of this function, let's call it y equals x minus 3. We know that the end behavior is going to be down to the left and up to the right. And we know that it's going to have a 0 at x equals 3. And so we can also use that to determine the positive versus negative branches of this function and the asymptote at its 0. So that's a good trick to know. Let's look at it in this case, where we actually have a quadratic in the denominator, x minus 3 quantity squared. That looks like this over here. I know I have a 0 at x equals 3. So on the graph of the rational function, that tells me I'm going to have an asymptote at that x value. And now we need to determine positive versus negative branches. Well, if you look at that red function, we only have positive y values for that function x minus 3 quantity squared. For that reason, we're only going to have positive branches over here. I'm still going to have my horizontal asymptote at at y equals 0. But in this case, both of my branches are going to be positive. They're both shooting up towards positive infinity, towards that asymptote, and then leveling out at 0. Now, if you're going to compare the shape to just a linear factor, the linear factors are a little more mellow. They are less abruptly curvy. So that's the main difference there, but the key idea is that they stick together. So compare that to this rational function with a quadratic denominator. This time, our denominator, the function x squared plus x minus 12, in factored form, x minus 3 times x plus 4, looks like this. So again, I know I'm going to have asymptotes where the function is equal to 0. So I'm going to get 2 of those. But now, again, think about the positive versus negative of the purple function. Well, it is positive to the left of that leftmost asymptote, so I get a positive branch of my rational function. Well, it's also positive to the right of my second asymptote there. So again, I know I'm positive there. And in the middle, the purple graph is always negative, and so I must get an always negative rational function down there. And again, I know it can't cross the y-axis because there is no x value in the numerator, so it cannot cross. It can never equal to 0. So again, we get that horizontal asymptote going through as well. But another way you could think of this is, again, we know the end behavior of the denominator is going to be up and up, so both of those ends are up. And I also know that the multiplicity of each of my zeros in the denominator is 1. And so that tells me that my branches are going to be on opposite sides because it's going to correspond to a cross. So I know at my left asymptote they have to be on opposite sides, and I know on my right asymptote they also have to be on opposite sides, branching off towards positive and negative infinity. And I just noticed that my graph with like the purple thing kind of looks like a creepy little monster. I actually just realized it kind of looks like a sad Kool-Aid man. I don't know what's making him sad, but oh, that's kind of weird looking. Okay, let's get rid of that. There we go. He's sad, but at least he's not creepy looking, but he should be red. So let's jump off to another example here. This one is a little bit different because now we're dealing with a cubic in the denominator, but that's okay because we can graph cubic functions. I know I have a 0 at positive 2, and the multiplicity of that 0 is 2, an even number, so that tells me it's going to bounce at that 0. I have another 0 at x equals negative 7, and I know the multiplicity is odd there, so it's going to cross. I know my end behavior is going to be down and up, and so I am going to come up, come through, come back down, bounce, and go back up like that. And now we can use this to get our rational function. Anywhere I had zeros, I am going to have vertical asymptotes. So there and there. Anywhere I'm negative, I'm going to have negative branches. Anywhere I'm positive, I'm going to have positive branches. That makes it really nice and quick to graph it. Another thing you can do is, if you're not feeling the whole graph on the denominator thing, you can just test some points. So you should know that we're going to get those asymptotes there at positive 2 and negative 7. So you can sketch those in, and then to figure out, you just need to figure out which side of the y-axis you are on, positive or negative. Which side of the x-axis is what I meant to say. So you could test a point. Like, for example, we know that leftmost 0 is happening at negative 7. So try to point to the left of it, like negative 8. Negative 8 plus 7 is a negative number, so that factor is going to be negative. And notice any x value from this factor is going to give me a positive value because of that exponent right there is 2. A negative times a positive is negative, so that tells me I have to be a branch diverging to negative infinity. And then you can just use the multiplicity of all the zeros from that point to figure the rest out, or you could continue to test points if that's what you prefer. So let's talk about the other aspect of rational functions that we are interested in, wholes. So if you think of this function x over x, well, that is absolutely the same as the function y equals 1, because x divided by x is 1, except for when x is actually equal to 0, because then we get a 0 in the denominator, and we know we cannot divide by 0. So I can say that this is the function y equals 1, except x cannot be equal to 0. So I'm going to get my whole right there, but everywhere else my function is just going to be the constant function 1. Okay, now it may not look like we've changed much by going to this problem, but it's actually going to look very, very different. First off, notice we have x minus 2 in the denominator. Well, we want to know, when is x minus 2 equal to 0? Well, add 2 to both sides. We are going to have a 0 at x equals 2. And you know that, but let's make sure we mark that 0. But think about these two functions. We have x minus 2, and we also have just y equals x. So if you think about it, my denominator is always going to be a little bit bigger than my numerator. Or rather, if you think about it like this, so if you think about the spot to the right of that 0, look at those fractions I just wrote down. Well, when x equals 2, we're dealing with the fraction 0 over 2. And then when x is 3, we have 1 over 3. Continuing on in that pattern, 2 over 4, 3 over 5. So we're getting positive fractions that are all just a little bit less than 1. And they're going to get closer and closer to 1 as x gets larger, but it never will be 1. So we're getting, you can think sort of a horizontal asymptote there, where it's going to level out towards 1. So that tells me I'm going to have a horizontal asymptote on my rational function when I graph it at the y value of 1. So now think about the zone in the middle there between x equals 0 and x equals 2. As your function is moving towards that asymptote, that vertical asymptote at x equals 0, because our denominator is equal to 0 there, the blue graph, remember, is our denominator. As we get closer and closer there, we are again going to shoot off to either positive or negative infinity, because of the whole dividing by small fractions thingy. But notice that our blue graph is positive and our purple graph is negative, and that tells me I'm going to have a negative number divided by a positive number, which gives me a negative number. So I know I'm shooting off towards negative infinity. So let's apply all this information now to this graph. I know I'm going to be coming in like that, and I'm going to redo that because I actually need to make sure I hit that 0, and I'm going to shoot down like that. So now think about that last area of this graph, where we're looking at x values that are less than 0. Notice that my blue and my purple graphs there are both negative, so I'm going to be having positive numbers. But also now look at how these fractions, since I'm dealing with a double negative there, I actually get the reverse effect as I had when x was greater than 2. I am getting fractions that are all greater than 1. So again, I know I'm going to level out towards that asymptote of y equals 1. But on the right side here, I am always greater than 1, so I'm on the other side of the branch. So I know that my graph is going to have to look something like this with that 0 at x equals 2, vertical asymptote at x equals 0, and a horizontal asymptote at y equals 1. So let's look at one final problem here. This function, it looks complicated, but it's not going to be too bad. We're just going to put everything together now. So let's go ahead and factor the numerator, and let's factor the denominator. So in the numerator, I'm going to get 5 times. Let's see how this factors. I have negative 21 and negative 4. So I'm thinking, what are factors of 21 that will combine to give me a 4? Well, 7 times 3 is 21, and negative 7 plus 3 is negative 4. So I know I have x minus 7 and x plus 3. Now in the denominator, I have x squared minus 6x minus 7, and that is going to factor as the only factors of 7 are 1 and 7, and the negative 6 is negative, so I know I have x minus 7 and x plus 1. Now, so let's piece it all together now. Recognize that we have a whole when x is 7. So that is going to eliminate. So really this is going to be the function 5 times x plus 3 over x plus 1 for x not equal to 7. It's a totally equivalent way to write that. That's going to help us know better what it looks like. So let's again think about this fraction, these two lines. I like looking at it as lines because then I can quickly determine what the fraction is going to be. So again, notice since my denominator x plus 1 has a 0 at negative 1, I know I'm going to have a vertical asymptote there. Since my purple function, aka my numerator, is 0 when x is negative 3, I know I'm going to have a 0 at negative 3. So now again, we just need to figure out what's going on in between those two important x values, to the right, in the middle, and to the left of those zeros of my numerator and denominator. So again, it's easy to really tell that when you have this little sketch here, because since my numerator is the purple and my denominator is that seafoam greeny thingy color, I don't know what that is, turquoise, whatever, I know that to the right of my asymptote, I am always going to be positive, since both of those lines are only positive y values. And I'm also going to be, if you're looking just at these lines, greater than 1, because my purple graph is above my green graph. But you have to also remember that I have this 5 there in my original function. So if you think about as you move farther and farther to the right, rather than having an asymptote at 5 that I'm approaching, I am going to have rather than having an asymptote at 1, I'm going to have an asymptote at 5. So I'm going to draw that into my graph as well. In between those two special x values, I am going to be negative, because if I look again at that graph, I'm on opposite sides of the x-axis there. So I'm going to be negative, and I'm going to come up, and I have to approach that 0, because I have to cross there. So I know that's going to look like that. I know this branch over here was looking something like that from what we did before. And then finally, I know that in this area right here, I am going to be positive and less than 5. So I'm going to come up here, and I'm going to try to approach that asymptote like that. And that is what my graph looks like. It doesn't look perfect because it's hard to draw on this thing, but that's what it is generally. So we have holes, we have vertical asymptotes, we have horizontal asymptotes, and we have zeros. So if you're anything like me, you forgot to include the whole at x equals 7. So please do not forget that. It is important. And I'll show you a better picture of what this looks like. well, it's underneath everything, so that's kind of weird. But you can sort of maybe tell. That's a little better. We have that hole at x equals 7 right there. And we have that horizontal asymptote at x equals 5. And we then also have that vertical asymptote running down the middle. Sweet.